Okay, good afternoon, everyone. So today let's continue our discussion about the basic series. I learned that you already finished 9.4 and started 9.5, I guess. So you have a bunch of technique tests for convergence or divergence, though I would like to give a quick recap of the concepts about series, right? And the basic tests that you can apply. And then probably on Wednesday, we can answer problems involving some of the fancier tests like integral test. What else? Comparison tests. I just finished 9.4. What does 9.4 cover? It covers the integral test and the basic comparison test. Is that correct? So you got those two tests in the bag. Then you will meet a lot more, some more tests like the ratio test, the limit comparison test, alternating series test, and so on. So there would be a bunch of them. So it would be, I think it would be better to look at them in conjunction with each other and how to distinguish which test to use if you are given a series and you were not specifically told to use a certain test. All right. So, but for today, let's go back to the basic and answer some problems about the basic test for divergence or convergence, right? And I guess last time we have seen this, the infinite number of mathematicians walking in a bar. So the first mathematician orders a beer. The second orders half a beer. The third orders a fourth of a beer, and so on. So it looks like the pattern is that the cake mathematician will order what? He will order, because here it looks like it's a to the power what? This is 1/2 to the power 0. This is 1/2 to the power 1. This is 1/2 to the this is 1/2 to the second power, and so on. Maybe it would be better to write the subscripts in terms of those powers. So let's try. Let's do A0 here, A1 here, A2. So AK would be 1/2 to the power K, right? Because it looks like that the mathematicians, being the nerd they are, they will order 1/2 to the power of their order in the list, right, or in the sequence. So basically, what the bartender did here is to, okay, there are infinitely many of you, each one ordering 1/2 to the K, where K is your position in the line. So it looks like all I need to prepare is the summation of a K's, K going from 0 to infinity, right? And if you expand this would be your 1 plus 1/2 plus 1/4 plus 1/8, and so on. But this is an example of a geometric series, right? So you can look at it as summation of 1/2 to the power K, K going from 1 to infinity. And the general form for a geometric series is summation of a r to the power n, and going from 0 to infinity. Let's change the index to k. I'm used to using n as the dummy variable, but it doesn't matter as long as you're consistent. You can use n, you can use k, or whatever your favorite letter is. But we have seen this. This is a geometric series. And a geometric series is convergent if the absolute value of r is less than 1, and it diverges otherwise. Okay. Now, in this particular case, we get k here. We got r equals 1/2, which is definitely less than 1. So this converges. And remember what convergence means. It is convergent if we get a finite value for the sum, right? So here, this theorem tells us that, okay, since a common ratio has magnitude less than 1, it should be convergent. So being convergent means we can expect to get a finite sum. our finite value for this sum. And actually, for convergent geometric series, the sum is equal to A over 1 minus R, right? A is the scalar multiplier. If you look at the specific problem that we have, A is equal to 1. So that's fine. So numerator is 1 over 1 minus R. So that's 1 minus the common ratio. So this would be 1 over 1/2 equals 2. And that's what the bartender concluded here. So he said that, okay, I'm just going to take away, I'm just going to put out two cups of beers, and that's sufficient for all of you guys. So it seems that the bartender himself is a mathematician here because he knows how to evaluate infinite series. Okay, so that's just an introductory example. The main point about series is to determine whether they are convergent or divergent. So a series is of the form a sub k, k going from 0 to infinity. Sometimes the index starts at 0, sometimes it will start at 1, though it doesn't matter, as you will see later. Now we say it is convergent if we can get a finite sum. And it will be divergent otherwise. It will be divergent in two ways. It can either mean, hold on, is my screen frozen for you guys? Yeah, let me try again. Yeah, because in my monitor it stopped, but I'm writing on my iPad. Let me share my screen again. Okay. Yeah, so this is the layman's interpretation of a convergent or divergent series. You have an infinite series. If you can get the finite sum, then it is convergent. If you cannot get the finite sum, either the sum will be infinite or there's no pattern at all, so we don't know what would the final sum be. It would be divergent, right? So for instance, let's look at summation of k going from 1 to infinity, right? So how do you expand the sigma notation or a summation notation? Well, you just plug in the starting value for k and then the next succeeding integers after it and then take their sum. So the summation starts from k equals 1. So we plug in k equals 1 here. So the first term is 1 plus the second term would be when k is equal to 2. Plug in k equals 2, we get 2. Third term would be 3, and so on, because we need to do it until infinity. So there would be an infinite amount of terms in here, but the pattern goes like this. We need to take 1 plus 2 plus 3 plus 4 plus 5 and so on until infinity, right? I'm using the until infinity in quotations, but essentially it would be a never-ending sum, right? And imagine what will happen. 1 plus 2 plus 3 plus 4 and so on. If you carry out the addition, we will not get a finite sum, right? It's impossible because the next number that we are adding to the sum is larger than the previous ones. And this sum will continue to grow until infinity. So there's no chance that we can get a finite sum here. So this is an example of a divergent series because we cannot get a finite sum at all, right? Now, if we look at this other example, say we got -1 to the n going from, say, 0 to infinity, okay? Then let's expand the summation. Well, the summation starts at n equals 0. Plug in n equals 0 here. We'll get what? We'll get -1 to the 0, which is 1. And then when n is 1, the next term, when n is 1, -1 to the 1 would be -1. Oops, sorry. Third term, n equals 2, will be -1 quantity squared. So that would be +1, -1, +1, -1, +1, and so on. What do you think will happen? Will I get a finite sum out of this infinite series? Any guess? Any idea? Will we get the finite sum out of this infinite series? Well, Kevin thinks so. He's suggesting we'll get to 0. How about the others? Well, I guess what Kevin did is to take the summation by pairs, right? So I guess his idea was, okay, I'm going to get negative 1. 1 minus 1, that's 0. 1 minus 1, that will be 0. 1 minus 1, that will be 0, and so on. And then it seems that you will just get an infinite bunch of zeros added together. You'll get a 0. And those sums are exactly 0, so there's no limiting process here, no complications about 0 times infinity. It will just be a bunch of zeros altogether, right? But if you do the summing up this way, if you say, okay, I'll add 1 plus 1, oops, plus 1 plus 1 plus 1. If I'll collect all the plus ones, I'll get an infinitely large number. And then I'll continue with I'll collect the negative ones, negative 1, minus 1, negative 1, minus 1, and so on. I'll get another very large negative number. So essentially, if I do the summation that way, I will have a very large number minus another very large number, which is indeterminate. So there's some sort of ambiguity here. So our layman's interpretation of convergent or divergent series should be modified a bit, or should be formalized to remove this sort of ambiguities, right? So the solution here is to adopt a formal definition of convergent series. So we say a series is convergent if the sequence of partial sums converges. It will diverge otherwise. Okay. So with this formal definition, I guess we can determine for certain if, from the point of view of this definition, this series will converge or not, right? So what do we mean by the partial sums? Well, the first partial sum is just you take the summation, one term. So that would just be your first term. That's n equals 0. Maybe I'll start at 0 here. When n is 0, we get positive 1. That's the first term. Then the second partial sum, S1, would be the sum of the first two terms. So it would be negative 1 plus 1. So it's going to be it would be 1 minus 1. The third partial sum, S2, would be 1 minus 1 plus 1. It would be 1. The fourth partial sum, S3, would be the sum of the first four terms. So that would be 0. S4 would be the sum from 0 until 4. So I'll have 1 minus 1 plus 1 minus 1 plus 1. So that would be positive 1, and so on. So if we look at the sequence of partial sums, we will have this. So you'll get 1, followed by 0, followed by 1, followed by 0, followed by 1, and so on. And is this sequence convergent or divergent? So now it should be clear that we're talking about two different sets of convergence. We have convergent sequences and convergent series. But the convergence of a series is defined in terms of the convergence of the sequence of partial sums. So in this case, this is our sequence of partial sums. Is it convergent or not? Anybody? What can you say about the limit of the sequence of partial sums? What is the limit of this sequence?
Does it oscillate? Oh, wait, is that the partial sum? Oh, that is the partial sum. What am I saying? It oscillates, so wouldn't it diverge?
Yeah, exactly. Correct, Robert. So this sequence of partial sums just oscillates between 1 and 0. We don't know for sure what will happen in the long run. Will it go to 0? Will it go to 1? Actually, it will not converge to either 1 or 0 because in the long run, they will still keep on oscillating, alternating between 0 and 1. So the limit doesn't exist because the terms in the sequence will not approach a single number as n approaches infinity. So the limit of the sequence of the partial sums does not exist. So that means, the sequence Sn diverges, so does the series. So the series of -1 to the n going from 0 to infinity is divergent via this definition. All right, because now we are defining the convergence of a series as the convergence of the sequence of partial sums. All right. So that removes all the ambiguity now. So we need not argue if this will converge or not. Based on the formal definition, this is divergent. Okay. So let me add another page here. Okay. Now here are the next actually the entire chapter will just revolve around determining whether a given series is convergent or not. So maybe let's give some properties that will help you in determining whether a series is convergent or not. So let's go to the basic series. So I guess we have seen earlier geometric series. So this is of the form a r to the n and going from 0 to infinity. You can now remember that this will be convergent if the absolute value of r is less than 1. So all you need to look for if you have determined that the given problem in your quiz or exam is a geometric series, all you need to look at is the common ratio. If the common ratio has absolute value less than 1, automatically it will be convergent. Otherwise, it will be divergent. Actually, in particular, if it is convergent, meaning the absolute value of the common ratio is less than 1, then the sum, or actually we have a formula for the sum. This would be equal to a over 1 minus r. Okay. So you need to identify what a is, the constant multiplier. This is a to the n. Okay. And then what the common ratio is, so you put that in the denominator. Okay. So all you need to know is a and r, then you're good to go. So you know the finite value of the infinite geometric series. Okay. Now another example would be the P series. I guess I can now give the P series because the proof of the convergence or divergence of the P series is based off of the integral test, and you were done with the integral test today. So P series look like this. So you have a summation n going from 1 to infinity of 1 over n to the p. The dummy variable is the base, and you have a constant p as an exponent. So P series are convergent if the value of p is greater than 1. Otherwise, it is divergent. Okay, a specific example of the P series is the harmonic series, which is the summation from 1 to infinity of 1 over n. So look at the base here. The base is the same as the indexing variable. And the exponent here is 1. That's a constant for all values of n. So this is a P series with P equals 1. And we already knew that if P is not greater than 1, then it is automatically divergent. So harmonic series or the harmonic series is divergent. Okay. But if you have summation of 1 over n squared, this is convergent because here it's a P series with P equals 2, which is greater than 1, right? So the summation of 1 over n squared is convergent because it is a P series with P greater than 1. Okay. What else? What are the other special series that you have seen? Well, we have what we call telescoping series. And for telescoping series, the middle terms will cancel each other out. So essentially, your infinite. Actually, maybe it's better to look at a specific example of a telescoping series where cancellation occurs. But the basic idea is that you have an AK minus 1, for instance. Sorry, plus. Let's make it plus 1. Robert, not necessarily only the first term, but some first few terms, and then probably some few terms in the end. So you will just have a finite number of terms. But the idea here is that some of the middle terms will cancel each other out, leaving you with just the first few terms and the last few terms. Okay. So yeah, maybe let's just discuss it later. I don't think there's a nice way of putting a generalization to it. But what I'll say for telescoping series is here, we need to look at the sequence of partial sums. And that's how we deal with telescoping series. Okay, let's go back to that later. And then what else? Let me insert another page here. Okay. Now we have what we call the basic test for divergence, which is a nice and very important theorem. Actually, it's very powerful. The basic test for divergence. It says that if you are given the summation of an and going from 1 to infinity, and if you take the limit of the n term and it is not equal to 0, then the series diverges. Okay. Later, you will be given a bunch of series, and you will be tasked to determine whether those series converges or diverges. Now, the first thing that you can do is to first take a look at the series, see if it's a geometric series, if it's a P series, or if it's a telescoping series, and then you can conclude convergence or divergence if they fall under any of those categories. But otherwise, the next best thing to do is the basic test for divergence. It's easy to do. Sometimes it's easy to be carried out mentally because all you need to do is to look at what is the term inside a summation. So you look at AM, take its limit as n approaches infinity, and if the limit is not equal to 0, then the series automatically diverges. So for instance, we have, I think the first example that we have, summation of k as k goes from 1 to infinity. The n term is k. So we take the limit of k as k approaches infinity. Obviously, that's infinity, not equal to 0, then that automatically diverges. And actually, I hope it makes intuitive sense to you guys why we can conclude divergence here. Because the limit of an not going to 0 as n becomes very, very large means that we will never run out of terms in the summation. So that means in the long run, we will keep on adding some things into our partial sum. So the sum will eventually grow and grow and grow because we will never run out of things to add to the previous sum. So that means there is really no chance that this series will have a finite value. because we will keep on adding numbers that doesn't approach 0 in the end. Now, just a little caveat here. If it happens that the limit of an is equal to 0, then no conclusions can be made. So, and then you need to make sure to try another test. Because if the limit happens to be equal to 0, there's a chance that the series will converge, and there's still a chance that it will diverge. For instance, remember the harmonic series 1 over n going from 0 to infinity, right? If you look at the n term, the limit of 1 over n as n approaches infinity is 0. But this is divergent, right? So here, limit of 1 over n going to infinity is equal to 0. And this is divergent, right? Because it's a harmonic series. But if you look at the p series 1 over n squared and going from 0 to infinity, actually, sorry about that. N cannot start at 0 because why? Because I'll have a 1 over 0 if I start at 0. So n, let's start n at 1. Okay. Here, the limit of 1 over n squared as n goes to infinity is also equal to 0, but the series is convergent, right? This is our example earlier of a convergent p series. So there's really a chance that if the limit of an is equal to 0, there's a chance that it would be divergent. There's a chance that it will be convergent. So the test for divergence does not apply when the limit is not equal to 0. Oh, sorry, when the limit is equal to 0. You need to try another test. Okay. And then just to cap this off, some more theorems. If you have a convergent series and you add to it another convergent series, the sum will of course be convergent. And this makes intuitive sense, right? Because if you have a convergent series, you'll have a finite answer to this, let's say L. If your second series is also convergent, you'll get another finite sum, which is M. So if you sum them up, you'll get L plus M, which is finite. So the sum would be convergent. On the other hand, if you have a convergent series plus a divergent series, then the answer or the sum would be divergent. So here you get a finite answer. Here you don't get the finite answer. So if you take their sum, it won't be finite. Okay, so that's why it's divergent. But if it's a divergent plus another divergent series, no conclusions can be made. All right. Now, if you have a constant c times a series, okay, the constant multiplier c won't affect the convergence or divergence of the series. This will converge if and only if the series without the scalar multiplier converges. So if this guy converges, then a scalar multiple of it will also converge. If this is divergent, then any scalar multiple when c is not equal to 0 will also diverge. So here maybe I'll put that qualifier, c is not equal to 0. Okay, and then the last thing that you can remember is two series that differ only in the first few terms. Either both converge or both diverge. Okay. So an example to this is that you have the summation of 1 over k plus 1. K going from 1 to infinity. Okay. Now, if we sum this up, this would be, if we expand this out, it would be 1/2 plus 1 plus 1/3, plus 1/4, plus 1/5, and so on, right? Which looks like the harmonic series, right? So which differs only, oops, from the harmonic series, which is 1 plus 1/2 plus 1/3 plus 1/4, and so on in the first term, right? So they are essentially the same except for the first term. The first term here is 1/2. Here the first term here is 1. Here the first term is 1/2, but they are similar with the rest of the terms in the summation, right? So they only differ with the first place. So that means they will both diverge because we already know that the harmonic series is divergent. Okay. So these are some of the basic tests that you can apply before we go to the complicated tests like the integral test, comparison test, limit comparison test, ratio test, what else? Nth root test, and so on. Okay. Now let's look at specific examples. Let's see. Oh, any questions so far?
None on this.
Mm-hmm. Yeah, let me see some problems here. Which one would be nice? Okay, let's try number 35.
I actually do have a problem from one of the homework.
Oh, sure. Yeah, you can. Yeah, you can send it in the chat, or you can dictate it to me if you can.
It's section 9.2, problem 28. So I was like, I thought n to the power of n grows faster than anything else, and then I put it in Desmos, and Desmos is saying that 3 to the power of 100n grows faster than n over n.
So you have n to the power n all over 3 to the 100n.
Yeah.
Let's see what happens here.
I assume at like term 1,000 that the top is greater, but she did say something in class about how something has to converge like timely or something like that for partial sums.
Yeah, actually here, what can we see? Because I also know that n to the power n grows fastest among all the powers. Because for instance, here I can treat this as n to the power n over 3 to the 100 to the power n. And so I can simplify this as what? I can write it as n over 3 to the 100 to the power n, right?
Yes.
And then when n is 3 to the... Well, this will be divergent because really the numerator grows a lot faster in the long run with 3 to the 100 to the power n. So I'm assuming you're working with sequences here and you're looking whether this sequence converges or not, right? This is convergence of sequences, right? So yeah, this will diverge. The sequence will not converge because in the long run, you'll get very, very large values. So because you might think, okay, 3 to the 100 is a very large number, okay? Because it's 3 times to itself 100 times. And then if you divide n by that, it seems that you'll get something close to 0. But remember, n goes to infinity. So when n is, say, it can grow very large. So it can be 3 to the 100 and 101. So that means this guy would be 3 to the 101 over 3 to the 100 raised to the 3 to the 101. So this would be 3 raised to the 3 to the 101, which is a very large number. So basically, this will still diverge because n to the n grows a lot faster than 3 over 100 to the n. Sorry, 3 to the 100n.
Okay, thank you.
All right. Yeah. At first look, that might not be the case because this has a very large exponent, right? But remember that n becomes a very, very large number. So in the long run, nothing beats n to the n. It will just take a matter of time before you reach there, but definitely n to the n will be at some point, or starting at some point, will grow a lot faster than any exponential function b raised to the power n. Okay. All right. So I hope that clears that up. So let's see. Okay. Let me see. Okay. Let's try problem 35. So here, for problems 25 to 42, the problem is to determine whether the following series converges or diverges. And if it will converge, then let's take the let's look at the sum if possible. All right. So let's look at problem 35. If you have also, if you already tried some of the problems from this worksheet and you encountered some problems, let me know. Tell me the problem number, or if you started doing the quizzes or the homeworks, and if you encountered some problems, just let me know. Okay, while waiting for that, let me try number 35. So for problem 35, it's 1 minus 2 to the k over 3 to the k as k goes from 0 to infinity. Now, at first glance, it will not fall under any of the categories that we have seen earlier, right? So it is not a simple geometric series, but it definitely kind of look like a geometric series. So let's try to manipulate the terms inside the summation and see if we can simplify it into a geometric series or a combination of geometric series. So here I can perform. I can split the sum up into two pieces. So I'm still inside this big summation, but I can write it as 1 over 3 to the power k minus 2 to the k over 3 to the k. So I just separated the two fractions, or I separated the difference into two fractions. And then I can use the properties of summation that allows me to distribute the summation inside of the terms, or basically to make it more let's analyze them probably separately and see what will happen. So if you look at the summation of 1 over 3 to the k going from 0 to infinity, you can write it definitely as the sum from 0 to infinity of 1 over 3 to the power k, which is now clearly a geometric series. It is a geometric series with a is equal to 1 because there is no multiplier there, right? And common ratio is 1/3. And the magnitude of r is less than 1. The common ratio has magnitude less than 1. So this series is convergent. And since this is a convergent series, we can find a finite sum, right? Remember, we have a formula earlier that says that if you are starting the summation at k equals 0, and you have a r to the power k, the sum will just be a over 1 minus r. Now, in this particular case, we mentioned that a is equal to 1. So a is 1. And then r is 1/3. So basically, this will become 1 over 2/3. And this would be 3/2, right? And there we go. We expected to get a finite sum because we have concluded that this is a convergent series because it's a geometric series with common ratio 1/3 with magnitude less than 1. And the finite sum, according to the formula, is equal to 3/2. Okay. Now, similarly, we can look at the second term. We have summation of 2 to the k over 3 to the power k. Right, that's our second term over here. Okay, I can write this as sum of 2/3 to the power k, k going from 0 to infinity, which is again a convergent geometric series with a equals 1 and common ratio equal to 2/3, which has magnitude less than 1. Okay, and so this will get a finite sum. Make sure that the summation goes from 0 before applying the formula. Summation starts at 0. The common ratio is raised to the power k, so all of the ingredients required in the formulas are here. So this is a over 1 minus r. A is 1. R is 2/3. So this is 1 over 1/3. So this is equal to 3. So therefore, the series that we started with, which is 1 minus 2 to the k over 3 to the power k, is convergent because it is the sum of two convergent series, right? So it is the sum of two convergent geometric series, and its sum is the sum of the sums of the two series. So this would be, what are the two sums? 3 halves plus 3, so that's going to be 9 halves. All right. Okay, Fatuma is suggesting one. Is this number 34 from this worksheet? So let me call it 34 as well. Summation from 0 until infinity of 3 to the power k minus 2 all over 2 to the 2k. Right. Now, now for this particular problem, Fatuma, we need to write it in the form of a geometric series. Kevin, I'm not sure what you're referring to as the sum minus sum, but what I'll do is to play with exponents, use properties of exponents here. So remember, the goal is to write it as a sum of a r to the k, k going from 0 to infinity. That's my final goal, right? So now to do that, what I'll do is, I need to keep a power k. So I'll write it as, okay, k from 0 to infinity. I want the 3 to the power k, but it has a 3 to the power k minus 2, so I'll have a 3 to the minus 2 here. So the numerator will look like this. Because if you multiply these two guys, loss of exponent tells us to take the sum of the exponents since we have the same basis, right? So this simplifies to this guy, right? On the other hand, playing with the loss of exponents in the denominator will lead us to have 2 squared to the power k, because this guy simplifies to that one. All right. And then now what we'll do here is this. I can write it now as 3 to the power k over 4 to the power k times 1 over 9, right? How do I get the 1 over 9? That came from 3 to the minus 2, right? And then 3k is over there. 2 squared is 4, so that's why I wrote just 4 in the denominator, okay? So now I can write it as summation of 1/9 times 3/4 to the power k, k going from 0 to infinity. So it is clearly now a geometric series with a equals 1/9 and common ratio is 3/4 with magnitude less than 1. So series converges. And we know the formula for the sum. It's 1 over 1 minus r because the summation started at 0, right? So a is equal to 1/9, r is equal to 3/4, So this would be 1/9 all over 1/4. So this would be 4/9. Okay, is that good, Fatuma? Oh, okay. Yeah, just be careful with that, okay? Let's see. Problem 35. So Kevin, you're referring to problem 35. Let me look at problem 35. Oh, that's the previous one that we that's the previous one we did. Yeah, we split the fraction out and look at it as two individual geometric series. Now let me try a different one. Let me try problem 37. Oh, sorry, k plus 2. Oh, but you'll get the answer to problem 37. What do you think, guys? Let me try problem 40. As much as possible, I'd like to answer the even numbered problems here because the odd problems has final answers in the textbook. So you can try them on your own and then check your answers with the textbook. So let's try problem 40. Though I might run out of time here, but problem 40 will turn out to be an will be a telescoping series. And let's see why. Now, I can do partial fraction decomposition here. So partial fraction decomposition will still haunt us here. So maybe I should do it this way. So note that 1 over k plus 2 times k plus 4 can be broken down into two partial fractions, a over k plus 2 plus b over k plus 4. So I'll do the same process as we did in the previous chapter in solving for a and b. So this will give me 1 equals a times k plus 4 plus b times k plus 2 for all k's. So I can give specific values for k. So in particular, I'm going to choose the killer values. If I let k equals -4, I'll get 1 equals -4. So this would be minus 2b. So that means b is -1/2. And then if k is equal to -2, I'll have 1 equals 2a. So that means a is 1/2. So that means our infinite series, 1 over k plus 2 times k plus 4, k going from 2 until infinity, can be written in partial fractions as 1/2 over k plus 2 plus -1/2 over k plus 4, k going from 2 to positive infinity. Okay, good. Oh, it's already time, so I need to pick up the pace here. But essentially, that's the process, partial fraction decomposition. Then I will factor the 1/2 out. There's a 1/2 here. There's also a 1/2 here. I can factor it all the way out of the summation. So we'll be left with 1 over k plus 2 minus 1 over k plus 4. This would be a telescoping series, and I will show you why. So let's look at the sequence of partial sums. Okay, so let's start with S2. I'll start with S2 just to match the index in the summation. So S2, that would be the sum of just plugging in k equals 2. So I'll have the 1/2, which came from here, times plug in 2. So I'll get 1/4 minus 1/6. That's S2. Then I'll take S3. S3 will be this guy. Okay, plus the thing that I'll get if I plug in k equals 3, right? That's the second partial sum. So when k is equal to 3, I'll get 1/5 minus 1/7. Okay. And then I'll take the next partial sum. Okay. I will add to this whatever I'll get if I plug in k equals 4. If I plug in k equals 4 here, I'll get 1/6 minus 1/8. And let's see if we get a pattern here. Well, here something starts to cancel each other out. So this 1/6 will be canceled by the 1/6 here. Okay. And then I don't think the pattern is clear yet, so let's carry on. Okay, let's go to S5. The partial sum S5 is basically obtained by adding to S4 whatever we get when k is equal to 5. When k is equal to 5, we get 1/7 minus 1/9, right? And let's see what happens here. Oh, I have a 1/7 here. I get another 1/7 there. Okay. And then let's see, is the pattern now obvious? Okay, it looks like 1/4 will never be canceled, right? Because what we expect in the next few turns will have higher denominators. So it seems that 1/4 will be a mainstay. It won't be canceled. 1/5 won't be canceled either because we already passed 1/5. Remember the pattern here is 4, 6, 5, 7, and then 6, 8, 7, 9. Then I guess the next one would be what? The next one would be 1/8 here, which will cancel the 1/8 over there, and so on, right? So essentially, the pattern will go this way. Maybe I'll expound on looking at deriving this pattern, but I hope it's clear that when you have Sk, the k term, again, it looks like 1/4 will remain. It won't be canceled, as well as 1/5, because yeah, 1/4 and 1/5 would be mainstays. 1/8 will be canceled by the next term, but essentially it looks like that we will be left with two negative terms. So here we'll have minus. For S5, we were left with 1/8 and 1/9. So it looks like the pattern here is this would be 1/k plus 3 minus 1/k plus 4. Let's see if that pattern holds. When k is 5, this would be minus 1/8, which is what we got there. When k is 5, this is negative 1/9, which is what we got there. Let's check with S4 if my conjecture is right. When k is equal to 4, this would be minus 1/7. Oh yes, I got the 1/7 there. When k is 4, this is minus 1/8, and there we go. It seems that those really would be the 4 terms that will remain. So that means the k partial sum is 1/2 times 4 terms, 2 positive terms, which is always 1/4 and 1/5. Because they are mainstays, they will not be canceled anymore. And then what will remain would be 2 negative terms in the end. And as we have seen in the patterns, it would be 1/k plus 3 and 1/k plus 4. So this would be the general formula for the partial sum. And then remember, the convergence of a series depends on the convergence of the sequence of partial sums. So we look at the limit of the k partial sum as k approaches infinity. So this would be 1/2 times this guy. Okay. But what will happen when k becomes large? When k becomes extremely large, this will go to 0. This will also go to 0. So eventually this is just 1/2 times 1/4 plus 1/5. So this would be 1/2 times 9/20. So this would be 9/40. All right. So I guess the challenge there is looking at the pattern for the telescoping series. So this is one example. I think who sent it earlier. I think it was Robert. Yeah, this is an example of a telescoping series wherein more than the first term and the last term remain. So, but the crucial thing here is most of the middle terms will cancel each other out, leaving us with the first few terms and last few terms. And then we take the limit of the partial sum, and then we get the finite answer, which is 9/40. Okay. Any questions with that, guys? So it's already way above time. So what I suggest is you try answering more problems from 9.3, 9.4, and then let me know on Wednesday if you have some problems on that. So I'll pick probably 3 questions from this worksheet. If you don't have questions, I'll pick 3 questions from this worksheet plus some bunch of problems from section 9.4. Okay? So I hope that sounds good. Any clarificatory questions before we end the meeting? None? Okay, so thank you guys for coming. Enjoy the rest of the day, and then let's see each other again on Wednesday. Bye, everyone.